22 years. That is how long it has been since the Western Pacific built a June typhoon as strong as the one churning over the Philippine Sea right now. Its name is Mekkhala, and in a little over a single day, it exploded, its winds climbing by nearly 60 miles an hour while forecasters watched, until it became the strongest June typhoon in more than 2 decades. And here is the part that should stop you. It is not done. As I speak, it is still feeding on the warm water, still tightening, still growing, and it has begun to turn toward Japan. The record is already broken. The storm that broke it is still getting stronger. The question is no longer how strong this gets. The question is what it means that the Pacific built a monster this early. If you want to understand what's really happening out there, subscribe to the Sky Lab, because we follow these stories from the first warning to the last. Drop a comment and tell me where you are watching from, and whether you have ever ridden out a storm like this one. Now, let's get into it. Part 1. The storm that wasn't supposed to be here yet. The calendar said June. The ocean said otherwise. Somewhere over the warm, open water of the Philippine Sea, east of the island of Luzon, a storm that started the week as an unremarkable cluster of thunderstorms has just done something the Western Pacific is not supposed to do this early in the year. In a little over a single day, it detonated. It went from a system forecasters were watching with mild interest to the strongest June typhoon this part of the world has seen in 22 years. Its name is Mekkhala, and as I'm recording this, it is still getting stronger, and it is turning toward Japan. Let me give you the number that stopped me when I first saw it, because it tells you almost everything you need to know about what kind of storm this is. In the 24 hours leading up to this, Mekkhala's maximum sustained winds increased by roughly 50 knots. 50 knots in one day. To put that in plain terms, the storm's winds jumped by nearly 60 miles an hour in the time it takes you to go to work, come home, sleep, and wake up again. Meteorologists have a formal definition for what they call rapid intensification, and the bar for that label is a gain of 30 knots in 24 hours. Mekkhala didn't just clear that bar, it cleared it by a margin that puts this event in the upper tail of everything we measure. Over a 36-hour stretch, the gain was closer to 70 knots. This isn't rapid intensification. This is something closer to explosive. When a storm does that, it earns a different kind of attention, and Mekkhala has earned it. By the time the intensification burst was finished, the system had climbed to the equivalent of a Category 4 hurricane, on the scale most of you know. At one point, forecasters clocked its maximum sustained winds near 95 knots, which is about 50 meters every second, with a central pressure that had fallen to roughly 935 hectopascals. And here is the part that matters. The official forecast from the Joint Typhoon Warning Center didn't have it stopping there. Their projection called for a peak intensity near 130 knots. 130 knots is the threshold at which this storm stops being called a typhoon and starts being called a super typhoon, and the forecasters left the door open for it to go even higher than that if the intensification rate held. So you have a storm that exploded overnight, reached major typhoon strength, and was still climbing toward the super typhoon line, all in the month of June. And the reason that word June keeps coming up, the reason I keep leaning on it, is that it is the strangest part of this entire story. Here is what you need to understand about the Western North Pacific, which is, for the record, the most active tropical cyclone basin on the entire planet. It produces more typhoons than any other ocean, and it produces the strongest ones. But it does that on a schedule. The peak of the season, the window when the basin manufactures its true monsters, runs from roughly August through October. That's when the ocean has spent an entire summer soaking up sunlight, when the heat stored in the upper layers of the sea is at its absolute maximum, when the atmosphere is most primed to let a storm reach its ceiling. June is the early season. June is supposed to be the warm-up act. June storms are usually weaker, sloppier, less organized, because the machine that builds the giants hasn't fully spun up yet. Mekkhala did not get that memo. And the way we know just how unusual it is comes down to that 22-year figure I mentioned, because that number isn't decoration. The last time the Western Pacific produced a June typhoon this strong, you have to go all the way back to the year 2004, more than 2 decades. An entire generation of storms has come and gone in between, and none of them, in this specific month, hit this specific mark. That's the headline that's rippling across weather coverage from Tokyo to Manila right now. Mekkhala becomes the strongest June typhoon in 22 years, and it heads toward Japan. But I want to be careful here, because I don't want you to walk away thinking this is only a story about a strong storm hitting a coastline. If that's all it were, it would still matter to the millions of people in its path, and we're going to talk about every one of them. But it would not be the reason I dropped what I was doing to make this video. The reason is bigger, and it's stranger, and it sits underneath the whole event like a question nobody has fully answered yet. The reason is that the Pacific just built a top-tier storm a full season ahead of schedule. And when an ocean does that, it is telling you something about its own state. It is telling you how much heat it is holding, how primed it has become, how loaded the machine is before the season has even really started. An early super typhoon is not just a storm, it is a readout. It is the ocean showing you its hand, and the hand the Pacific just showed us, in the third week of June, is not the hand of a calm and ordinary year. Let me set the scene for you the way it actually unfolded, because the timeline is part of what makes this so unsettling. Earlier in the week, this system was a developing tropical cyclone moving across the warm waters east of the Philippines. When it entered the zone that the Philippine Weather Agency, PAGASA, is responsible for monitoring, on the 20th of June, they gave it a local name, the way they always do for storms in their waters. They called it Francisco. On the international naming list, the one used across the whole basin, it carries the name Mekkhala. And in the cold, technical language of the warning centres, it is simply storm number 7 of the Western Pacific season, designation 07W. 3 names for one storm depending on who's talking. Keep that in mind because it matters later when we get to the people claiming the real story is being hidden. For its first day or two as a name system, Mekkhala behaved. It was a tropical storm, then a typhoon, moving generally west-northwest. The kind of track that, in a different setup, might have carried it toward land. But it stayed offshore, and then, on the 22nd of June, the floor dropped out from under the forecast. The storm found exactly the conditions it needed, and it began to feed. I want you to picture what rapid intensification actually looks like, because it is one of the most genuinely frightening things in all of atmospheric science, and most people have never had it explained to them. A weak tropical storm is a disorganized thing. Its center is broad and wobbly, its thunderstorms are scattered, its structure is loose. When rapid intensification kicks in, all of that changes, and it changes fast. The storm pulls itself together, a clear eye opens at the center, a calm column of sinking air ringed by the most violent winds on the planet. The thunderstorms organize into a tight symmetrical wall around that eye. The pressure at the center collapses, and as it falls, the winds racing in toward that low pressure accelerate. Because the steeper the pressure drop, the harder the air is squeezed inward and the faster it has to move. It is a feedback loop, a storm bootstrapping itself into a monster, and once it gets going under the right conditions, very little can stop it except running out of fuel or running into land. Mekkhala got going. And it did not run out of fuel, because the patch of ocean it was sitting on was holding more than enough. Now the storm is positioned in the Philippine Sea, east of Luzon, and I need to make one thing clear right away because it matters enormously for tens of millions of people. Mekkhala is forecast to stay away from a direct hit on Luzon. It is not, in the current projection, going to plough into the northern Philippines as a landfalling super typhoon. That is genuinely good news, and it is the result of the storm curving northward, away from the islands, rather than continuing west into them. The Philippines are not getting off completely free, and we'll talk about what they are facing, but the nightmare scenario of a Category 4 or stronger storm coming ashore over Luzon is not what the models are showing. Instead, the storm is turning. It is beginning the long, sweeping curve that Western Pacific storms so often make, the turn that takes them north and then northeast, and aims them at a very different target. That target is Japan. The forecast track carries Mekkhala across the open Philippine Sea and toward the southern islands of Japan, the long chain known as the Ryukyus that stretches southwest from the main islands toward Taiwan. The first places in the crosshairs are the Sakishima Islands, the southwestern end of that chain, and then Okinawa, the largest and most populated island in the group, home to more than 1 million people and to some of the most significant infrastructure in the region. The window for the closest approach is around the 25th and 26th of June. After that, the projections take the storm, weakening now on toward the waters south of Japan's main islands, in the direction of Tosa Bay on the island of Shikoku. So this is the shape of the thing. A storm that exploded overnight into the strongest June typhoon in 22 years, still intensifying toward the super typhoon line, now curving away from the Philippines and setting its sights on Okinawa and the Japanese mainland within days. That is the event. That is what is happening right now as you watch this. But I told you the real story sits underneath the event, and it does, because every piece of what I just described raises the same question, and it is the question this entire video is built around. Why now? Why is the Pacific producing this kind of storm in June, a month it normally reserves for the warm-up? What does it mean that the ocean is this loaded this early? And if a single patch of sea east of the Philippines can build a near super typhoon before the season has even hit its stride, what exactly is the rest of that season going to look like? To answer that, we have to go inside the storm. We have to understand what made Mekkhala blow up the way it did, because the ingredients that fed it are the same ingredients that tell us how primed this ocean has become. And once you see those ingredients laid out, the 22-year record stops looking like a freak accident and starts looking like a warning. So let's go into the machine, and let's start with the part that surprised even the people whose job it is to forecast these storms for a living. Part 2. Anatomy of an explosion. Forecasters do not scare easily. The people who track these storms for a living have seen thousands of them, and they speak in calm, measured, almost bureaucratic language, because their job is to be the steady hand when everyone else is panicking. So when their own forecasts start using words like rapid intensification, and when their projected numbers climb hour after hour without leveling off, you should pay attention, because the calm professionals are quietly telling you that something out of the ordinary is unfolding. What happened to Mekkhala on the 22nd of June is the single most dangerous behaviour a tropical cyclone can exhibit, and it has a name that sounds almost gentle for what it actually is. Rapid intensification. I gave you the textbook definition a moment ago, a gain of 30 knots in 24 hours. But I want to sit with that definition for a second, because it was written to describe the exception, not the rule. Most storms never do it. Most storms strengthen gradually, in fits and starts, gaining and losing organisation as they wobble across the ocean. Rapid intensification is the rare, violent exception. The cases where everything aligns and a storm goes from manageable to catastrophic, faster than the human systems built to warn people can keep up. Mekkhala gained about 50 knots in 24 hours, and roughly 70 knots in 36. So it didn't sneak across the rapid intensification threshold. It blew through it at nearly twice the defining rate. And I want you to understand why that specific behaviour, that speed, is the thing that keeps emergency managers awake at night, because it is not really about the final wind speed. It is about the clock. Think about what a coastal community needs in order to survive a major storm. It needs time. It needs time to issue warnings, time to open shelters, time for people to board up homes, gather supplies, decide whether to leave and actually get out. That entire chain of survival depends on knowing, in advance, that a serious storm is coming, and roughly how strong it will be. Now imagine a storm that is a middling tropical system one evening and a Category 4 monster the next morning. Every hour that the storm spends exploding is an hour that the forecast for its final strength is racing to catch up. Communities that went to sleep being told to expect a strong storm can wake up in the path of a catastrophic one. That gap between what people were told to prepare for and what actually arrives is where rapid intensification kills. History is full of storms that did exactly this, that bloomed in the final hours before landfall and caught populations expecting something far less. The wind speed is the weapon. The speed of intensification is what loads it. So let's go inside Mekkhala and look at the machinery of that explosion. Because once you understand how a storm pulls this off, you'll understand why the conditions it found are the real story. A tropical cyclone is, at its core, a heat engine. That is not a metaphor, it is a literal description of the physics. The storm takes heat energy out of warm ocean water, converts it into the mechanical energy of wind, and exhausts the spent air out the top. Warm water at the surface evaporates, lifting enormous quantities of water vapour into the storm. As that vapour rises and cools, it condenses back into liquid, into the towering thunderstorm clouds that make up the body of the system, and condensation releases heat, the same latent heat the ocean put in when it evaporated the water in the first place. That released heat warms the core of the storm. The warm core lowers the air pressure at the centre, and the falling pressure pulls in more air, more moisture, more fuel. Round and round it goes. The warmer the water, the more fuel the engine has, and the harder it can run. Now, here is the elegant and terrible part. The strength of that engine is governed by a few specific conditions, and when all of them line up at once, the storm can run at maximum output. Mekkhala found all of them lined up. The first and most important is the ocean itself, the fuel, and we're going to spend an entire chapter on that one because it is the key to this whole story. But the ocean alone is not enough. A storm can be sitting over bathtub warm water and still fail to organise if the atmosphere around it is hostile, and the most common way the atmosphere fights a storm is through something called wind shear. Wind shear is the change in wind speed or direction as you go up through the atmosphere. Picture the storm as a tall, stacked column of spinning thunderstorms, reaching from the ocean surface up to the edge of the stratosphere, 10 or 12 miles high. For that column to intensify, it needs to stay vertically stacked, the top sitting neatly over the bottom, so that the warm core can build and the whole structure can tighten. Now imagine strong winds blowing at the top of that column in a different direction than the winds at the bottom. Those upper winds shove the top of the storm sideways, off-centre from the base. The column tilts, the warm core gets ventilated, smeared out, disrupted. The engine can't build its pressure. Wind shear is the single most reliable storm killer in the tropics, the thing that takes a promising system and tears its head off before it can become dangerous. Mekkhala had almost no shear to fight. The vertical wind shear around the storm was measured at something like 12 to 17 miles per hour, which in this context is wonderfully, dangerously low. The column could stand up straight, it could stack vertically and stay there. Nothing was knocking its head off, and a storm that can stand up straight over warm water is a storm that can reach its potential. Then there is the exhaust. Remember, this is a heat engine, and every engine needs to vent its exhaust or it chokes. For a tropical cyclone, the exhaust is the air flowing outward at the very top of the storm, the outflow. All that air rising up through the eye wall has to go somewhere, and if it can spread out and escape efficiently at the top, the storm can keep pulling more air up from below. If the outflow is blocked or sluggish, the storm backs up on itself and can't intensify. Mekkhala had excellent outflow. The reports describe strong upper-level venting aided by what's called a point source aloft, which you can think of as a favourable channel in the upper atmosphere that grabbed the storm's exhaust and carried it away efficiently, like a chimney with a perfect draft. Warm water below, no shear to tilt the column, and a clean chimney up top. That is the recipe for explosive intensification, and Mekkhala had all three at the same time. This is why the storm did what it did. It wasn't random and it wasn't bad luck. It was a near-perfect alignment of conditions, and when those conditions align over the most active tropical basin on Earth, you get exactly this. You get a storm that detonates. And I want to point out something about that alignment because it connects to the question we keep circling. Two of the three ingredients, the low shear and the strong outflow, are atmospheric. They come and go. They are about the weather of the moment, the particular setup of winds in the upper air on this particular week. Those things happen. They're not unusual on their own. But the third ingredient, the ocean heat, is different. The ocean is not the weather of the moment. The ocean is the slow, deep memory of the climate. The temperature of the sea surface in June reflects months and years of accumulated energy, and it changes far more slowly than the winds aloft. So when a storm finds water this warm, this early, it isn't a fluke of the week. It is a statement about the state of the basin. And that is the ingredient we have to examine most closely, because the heat that fed Mekkhala is the heat that's going to feed everything that comes after it. Before we go there, let me give you one more piece of the picture, because it sharpens just how fast this happened. When a storm intensifies this rapidly, the visual transformation on satellite is stunning and a little eerie. In a matter of hours, you watch a ragged asymmetric swirl tighten into a clean circular system with a sharp, distinct eye punched through the centre. Forecasters watching the satellite imagery of Mekkhala saw exactly that. The rapid emergence of a well-defined eye, the symmetry locking in, the cloud tops getting colder and colder as the thunderstorms punched higher into the atmosphere, all the classic signatures of a storm hitting its stride. To the trained eye, that imagery is a storm announcing that it has found everything it needs. Now, the Joint Typhoon Warning Center, the United States military forecasting body that tracks these Western Pacific storms, put a specific projection on where this was heading. They forecast the peak intensity to reach around 130 knots, the super typhoon threshold, and they noted that if the rate of strengthening continued, it could push past that. 130 knots of sustained wind is the kind of storm that flattens structures, strips vegetation to bare ground, and rewrites coastlines. The fact that a June storm was being forecast to reach that mark is, again, the part that doesn't fit the calendar. It is the kind of intensity the basin is supposed to reserve for the heart of the season months from now. There is genuine uncertainty in these numbers, and I want to be honest about that, because honesty is the whole point of this channel. The intensity of a storm sitting in the open ocean, far from any instruments, is largely estimated from satellite imagery using established techniques. There is real uncertainty in that estimate, and different agencies looking at the same storm can arrive at somewhat different numbers. We'll come back to that uncertainty later, because some people online are going to use it to argue that the truth is being hidden, and the reality is far more interesting than that. But the uncertainty does not change the core fact, the fact that every agency watching this storm agreed on. Mekkhala underwent explosive rapid intensification and became the strongest June typhoon in more than 2 decades. That is not in dispute. The only argument is about the precise size of the monster, not about whether the monster is there. So we have our storm and we understand the machinery of its explosion. We know it found low shear and a clean chimney, the atmospheric ingredients that come and go. And we know it found something else, the deep ocean fuel, the ingredient that doesn't come and go, the ingredient that reflects the state of the entire basin. That fuel is where the real story lives, and it's where we're going next, because to understand why this storm is a warning and not just a weather event, you have to understand exactly how much heat the Pacific is holding right now, and why that heat is sitting there in June when it has no business being this intense. Let's go look at the water. Part 3. The fuel beneath the storm. Everything about Mekkhala comes back to the water. The shear and the outflow open the door, but the ocean is what walked through it, and the ocean is the part of this story that should make you sit up, because the ocean is the part that isn't going anywhere. So let's talk about the sea surface temperature beneath this storm, because the number is the quiet centre of this entire event. The waters that Mekkhala intensified over measured between 29 and 30 degrees Celsius. In the units many of you use, that's roughly 84 to 86 degrees Fahrenheit. Bath water. Warm enough to swim in without a flinch, and that warmth is not a detail. It is the fuel tank, and it was full. Here's the reference point that makes the number mean something. There is a rough threshold that scientists use as the minimum sea surface temperature needed to sustain a tropical cyclone, and that threshold sits at about 26.5 degrees Celsius, around 80 degrees Fahrenheit. Below that, the engine starves. The evaporation isn't strong enough, the heat isn't there, and storms struggle to organise or hold together. That 26.5 degree line is the floor, the bare minimum. Mekkhala wasn't sitting near the floor. It was sitting over water 3 to 4 degrees Celsius above it. And in the world of tropical cyclones, 3 to 4 degrees of extra ocean warmth is not a small bonus. It is the difference between a storm that can reach maybe a modest typhoon strength and a storm that can explode into the upper categories. Every fraction of a degree of extra heat is more fuel, more evaporation, more energy available to the engine, a higher ceiling for how strong the storm can ultimately become. And it gets more important than just the surface, because here is a subtlety that most coverage skips and that you really need in order to understand why this storm got so strong so fast. The temperature of the very top skin of the ocean is only part of the story. What matters even more for a powerful, slow-moving or intensifying storm is how deep that warmth goes. Scientists measure something called ocean heat content, which is essentially the total amount of warmth stored not just at the surface, but down through the upper layers of the sea. The reason this matters is that a strong storm is a violent mixer. Its winds churn the ocean, dragging up water from below. If the warm layer is shallow, the storm quickly pulls cooler water up to the surface beneath itself and effectively cuts off its own fuel supply, a kind of self-limiting break. But if the warm layer is deep, if there's a thick reservoir of heat extending well below the surface, then the storm can churn all it wants and keep finding warm water. The break never engages. The fuel keeps coming. And storms sitting over deep, warm ocean heat content are exactly the storms that undergo the most extreme rapid intensification, because nothing stops them from feeding. The fact that Mekkhala intensified the way it did, fast and far, is itself evidence that the warm layer beneath it was not shallow. A shallow warm layer would have braked the storm. This storm did not get braked. It accelerated. That tells you the heat ran deep. Now, step back and ask the question this whole video is circling. Why is the Pacific holding this much heat, this deep, in June? And this is where Mekkhala stops being a weather story and becomes a climate story, because the answer involves the larger state of the ocean, the slow background conditions that set the stage for every storm that forms. Let me bring in something we've talked about on this channel before, in our recent coverage of the shifting state of the Pacific. The tropical Pacific Ocean swings between warm and cool phases in a cycle that governs weather patterns across the entire planet. You've heard the names. The warm phase is El Niño. The cool phase is La Niña. Scientists track where we are in that cycle with an index, a single number that tells you how far above or below normal the central Pacific sea surface temperatures are running. And right now, that number is telling a specific and important story. As of this spring, that index sat at about plus 0.48. In the technical language, that's still in the neutral range, not yet officially El Niño, but it is neutral leaning warm, and crucially, it is warming. And the trajectory is the part that matters. Go back to late last year, to the final months of 2025, and that same index was sitting at around minus 0.55. That's the cool side, the La Niña leaning side. So in roughly 6 months, the tropical Pacific swung from minus 0.55 to plus 0.48. It crossed from the cool side of neutral toward the warm side, climbing toward the El Niño threshold, and it did it quickly. The sea surface temperatures in the key region of the Pacific climbed to around 28 degrees Celsius. The ocean has been warming, steadily and significantly, right through the spring and into the start of summer. And that is the backdrop against which Mekkhala formed. A Pacific that has been heating up, building its reservoir, climbing toward a warmer state, all in the months leading up to this storm. When you put a developing typhoon over an ocean in that condition, an ocean that is warm at the surface and warm at depth and trending warmer, you have set the stage for exactly the kind of explosive intensification we just watched. The basin was primed. Mekkhala is what a primed basin produces. I want to be very careful and very honest here, because this is exactly the kind of moment where it would be easy to overclaim, and overclaiming is the fastest way to lose your trust. So let me draw the line clearly. No single storm can be blamed on the broad state of the ocean. Mekkhala intensified because of the specific conditions it found in a specific place at a specific time, the warm water, the low shear, the good outflow. Those local conditions are what built this storm, and on a different week, with more shear, the same ocean might have produced nothing remarkable. Weather is the roll of the dice, but the state of the ocean, the warmth of the basin, the depth of the heat, the warming trend that is the loading of the dice. It doesn't determine the outcome of any single roll, it changes the odds, and what Mekkhala is telling us, what the 22-year record is telling us, is that the dice in the Western Pacific right now are loaded toward the high end. This is the framework scientists use to think about the relationship between individual storms and the warming ocean, and it's worth holding on to because it cuts through a lot of confusion. You cannot point at one storm and say the ocean's warmth caused it. But you can look at the broader pattern, the frequency of these explosive intensification events, the calendar window in which the strongest storms appear, the ceiling that storms are able to reach, and you can ask whether that broader pattern is shifting. And there is a substantial and growing body of research asking exactly that question, examining whether warming ocean surfaces and rising ocean heat content are making rapid intensification more common and pushing the season's most dangerous storms into a wider stretch of the calendar than they used to occupy. Mekkhala is a single data point. I'm not going to stand here and tell you one June typhoon proves a trend, because it doesn't, and anyone who tells you a single event proves anything is selling you something. But I will tell you this, Mekkhala is precisely the kind of event that fits the pattern the research has been describing. An early season storm forming before the calendar peak, finding water warm enough and deep enough to support explosive intensification, reaching a strength that the historical record says should require the heart of the season. It is a data point that lands exactly where the warming ocean hypothesis predicts data points should increasingly land. One point doesn't make a line, but you should notice when a point lands right on the line that scientists drew years ago. Let me give you a way to feel the scale of the energy we're talking about, because the abstraction of degrees and indices can hide just how staggering the forces are. A mature tropical cyclone, a storm like the one Mekkhala became, releases heat energy at a rate that dwarfs human power generation. The released energy from the condensation in a single large typhoon, every single day, is on the order of hundreds of times the total electricity generating capacity of the entire human race. We have never built anything that produces power on the scale that one of these storms produces it casually, continuously, just by existing over warm water. And the source of all that power is the heat in the ocean. That is what the sea surface temperature number represents. It's not just a measurement, it's a measure of how much fuel is available to be converted into the most powerful weather events the planet can produce. And right now, in the Western Pacific in June, that fuel gauge is reading high. There is one more piece of the ocean story I want to give you, because it connects directly to where this storm is going. The warm water doesn't stop at the Philippine Sea. The warmth extends across a broad swathe of the Western Pacific, including, to a significant degree, along parts of the path the storm is going to follow as it curves north. Now, as a storm recurves toward higher latitudes, it generally moves over progressively cooler water and into a zone of stronger wind shear, and that's the main reason the forecast calls for Mekkhala to gradually weaken as it heads toward Japan rather than to keep strengthening all the way to landfall. That weakening is real, and it is genuinely good news for the people in its path. But the degree of that weakening depends heavily on exactly how warm the water remains along the track and how quickly the shear ramps up, and those are precisely the variables that carry uncertainty. A storm that holds its warmth a little longer or finds the shear a little weaker than expected arrives stronger than forecast. We have all seen storms that were supposed to weaken before landfall and didn't weaken nearly as much as hoped. So while the most likely scenario has Mekkhala coming down from its peak before it reaches Okinawa and the Japanese seas, the warm ocean that built it is also sitting in part along its path, and that is a variable worth watching closely over the next few days. Let me give you a way to picture the difference between a shallow warm layer and a deep one, because it's the single most important thing for understanding why some storms fizzle and others explode. Imagine 2 pots of water on a stove, both heated to the same temperature at the surface. In the first pot, only the top inch is warm and everything below it is cold. In the second pot, the warmth runs all the way to the bottom. Now drop an ice cube into each and stir. The first pot cools almost instantly, because there's barely any heat there to begin with, just a thin, warm skin sitting on cold water. The second pot shrugs the ice cube off because there's a deep reserve of warmth to draw on. A typhoon is the stirring. Its winds churn the sea violently, dragging up whatever is below. A storm over the first pot cools its own fuel and stalls. A storm over the second pot stirs all it wants and keeps finding heat. Mekkhala was sitting over the second pot. The Western Pacific is famous for exactly this kind of deep, warm reservoir. There's a region scientists sometimes refer to as the warm pool, a stretch of the tropical Western Pacific that holds the warmest open ocean water on the planet, and it holds that warmth not just at the surface, but down through a thick layer of the upper ocean. This is part of why the basin is the most prolific producer of intense tropical cyclones in the world. It's not just that the surface is warm, it's that the warmth has depth, a foundation that storms can draw on without quickly exhausting it. When a developing system finds itself over a deep, warm layer with low shear and good outflow, the brakes that would stop a storm elsewhere simply aren't there, and the system can run all the way up to its ceiling. That's the physical setting Mekkhala exploited, and it's a setting the Western Pacific offers more readily than any other ocean on Earth. And here is why the depth of the warmth connects back to the larger state of the basin, the thing we keep circling. Surface temperatures can be warmed quickly by a stretch of sunny, calm weather, a temporary thing that comes and goes. But deep ocean heat, warmth stored through a thick layer of the sea, accumulates slowly over months and years, and it reflects the longer-term energy budget of the ocean rather than the weather of the week. So when a storm intensifies in a way that reveals deep warmth beneath it, as Mekkhala did, it's revealing something about the slow, accumulated state of the basin, not just a lucky warm patch. The depth of the heat is the memory of the ocean, and the memory the Western Pacific is carrying right now into the start of this season is a warm one. That's the foundation the rest of the season will be built on, and it's why a single storm's behaviour can tell you something real about the months still ahead. So this is the fuel. Warm water, 3 to 4 degrees above the minimum, running deep enough to resist the storm's own churning, sitting over a basin that has been warming for months and climbing toward an even warmer state. That is what Mekkhala fed on. That is why it exploded. And that is why I keep insisting this is more than a weather story, because the fuel that built this storm is a property of the entire basin, not just one patch of sea, and the entire basin is going to be sitting here, warm and loaded for the whole season ahead. Now we know what the storm is, and we know what built it. The next question is the one that millions of people in southern Japan are asking right now with a great deal more urgency than the rest of us. Where exactly is it going? Because a storm that explodes in the open ocean is a fascinating piece of science, but a storm that curves toward a chain of inhabited islands is something else entirely. So let's follow the track. Let's understand the invisible force that's steering this thing, and let's talk honestly about what Okinawa, the Sakishima Islands, and mainland Japan are facing over the next several days. Part 4. The turn toward Japan. A storm does not choose where it goes. It is steered, pushed across the ocean by forces far larger than itself, and to understand where Mekkhala is heading, you have to understand the invisible hand that's guiding it. That hand is a ridge of high pressure, and the way it's positioned right now is the reason this storm is curving toward Japan instead of ploughing into the Philippines. Let me explain how this works, because once you see it, you'll be able to read the track of almost any Western Pacific storm. Out over the subtropical ocean, there sits a semi-permanent dome of high pressure, a vast region of sinking air that the forecasters call the subtropical ridge. Air flows around the edges of that ridge in a clockwise direction in the northern hemisphere, and tropical cyclones, which can't punch through the ridge, get carried along its edges like a leaf caught in the current at the rim of a slow whirlpool. When a storm is on the southern flank of the ridge, that clockwise flow pushes it generally westward, which is why so many Western Pacific storms start out heading toward Asia. But when the storm reaches the western edge of the ridge, the flow there curves it northward, and then, once it's on the northern side, it gets carried back toward the east. That whole sweeping path, west, then north, then northeast, is what forecasters call recurvature, and it is the single most common shape a Western Pacific typhoon track takes. Mekkhala is recurving. For the early part of its life, it rode the southern edge of a subtropical ridge centered to its northeast, which pushed it west-northwest toward the Philippines. But it is now reaching the western edge of that steering ridge, and the flow is turning it. The storm is beginning to curve north, and the forecast carries it through that northward turn and then bends it toward the northeast, away from the Asian mainland and out toward the islands of southern Japan. This is why the Philippines, despite having the storm sitting right off their coast, are forecast to avoid a direct major typhoon landfall. The ridge is releasing Mekkhala northward before it can come ashore over Luzon. And this is also why the timing of that turn matters so enormously, because the exact moment the storm begins to recurve determines how far west it gets before it heads north, and that, in turn, determines exactly which islands end up under the worst of it. A turn that comes a little earlier keeps the storm further east, out over open water. A turn that comes a little later carries it further west, closer to Taiwan and the southwestern Ryukyus. Small differences in the timing of recurvature translate into large differences in who gets hit and how hard. This is the kind of forecast detail that emergency managers across southern Japan and Taiwan are watching hour by hour right now, because their preparations depend on it. Here is the track as it currently stands. Mekkhala is forecast to continue moving generally west-northwest over the next day or so, at a forward speed of around 20 km per hour, possibly strengthening further during that window. Then it makes its turn, curving north and then northeast across the Philippine Sea. The path aims it toward the southern islands of Japan, and the first land in the firing line is the Sakishima Islands, the southwestern tip of the long Ryukyu chain that arcs between Taiwan and the Japanese mainland. The window for the storm's approach to the Sakishima Islands and then to Okinawa's main island is centered on the 25th and 26th of June. After it passes the Ryukyus, the projections carry the weakening storm onward toward the waters south of Japan's main islands in the direction of Tosa Bay on Shikoku, where it is expected to continue losing strength. Let me tell you about the places in that path, because these are not empty dots on a map. Okinawa is home to more than 1.5 million people. It is a dense, developed island with cities, ports, and critical infrastructure, and it sits in one of the most typhoon-exposed locations on Earth, which means its buildings and its people are, thankfully, far more prepared for these storms than most coastal populations anywhere in the world. Okinawa knows typhoons, its construction codes, its emergency systems, its cultural memory of these storms are all built around the expectation that powerful typhoons will come. That preparedness is genuinely protective, and it's one of the reasons a storm that would be catastrophic elsewhere can strike Okinawa and be weathered, if not without damage, then at least without the kind of mass casualties that an unprepared coastline would suffer. But preparedness is not invulnerability, and a storm of this potential strength is a serious threat even to a place that knows typhoons as well as Okinawa does. The hazards stack up in layers. There is the wind, of course, capable of damaging structures, downing power lines, and turning loose objects into projectiles. There is the storm surge, the wall of seawater that a typhoon's winds push ahead of it onto the coast, which is often the deadliest part of any tropical cyclone. There is the rainfall, which can be measured in feet rather than inches with a storm this size, bringing flash flooding and landslides, particularly in the steep terrain of the islands. And there are the seas, the enormous waves a storm like this generates, which threaten shipping, ports, and anyone near the coast. For an island chain, the ocean hazards, the surge and the waves, are especially dangerous because there is nowhere on an island that is truly far from the sea. The Sakishima Islands, at the southwestern end of the chain, are smaller and less populated than Okinawa's main island, but they are closer to the storm's projected path and could see the closest approach of the strongest winds, depending on exactly how the recurvature plays out. The people there are watching the forecast with the same intensity as anyone, because for them, the difference between the storm passing 50 miles to the east or 50 miles to the west is the difference between a serious storm and a survival situation. Now, I told you the storm is forecast to weaken as it approaches, and I want to come back to that, because it's the most important piece of good news in this entire forecast and I don't want it to get lost. As Mekkhala recurves north, it moves over gradually cooler water and into an environment with more wind shear, the same shear that, in abundance, tears storms apart. That combination is expected to pull the storm down from its peak intensity before it reaches the Ryukyus, so the storm that arrives at Okinawa is most likely not going to be the same monster that's churning over the Philippine Sea at peak strength right now. It will probably be weaker. That is real, and it matters, and it's why the forecast is serious rather than apocalyptic. But, and you knew there was a but, the degree of that weakening is one of the genuine uncertainties in this forecast, and I would be doing you a disservice if I pretended otherwise. How much a recurving storm weakens depends on exactly how cool the water gets along its path, exactly how much shear it encounters, and exactly how fast it's moving when it gets there. A storm that recurves over water that stays warmer than expected, or that encounters less shear than forecast, arrives stronger than the headline forecast suggests. The history of tropical cyclones is full of storms that were supposed to weaken before landfall and stubbornly refused to cooperate. So the responsible way to read this forecast is not let your guard down. The storm will fall apart before it gets here, but rather, the most likely outcome is meaningful weakening. But a stronger than expected arrival is well within the range of possibility, so prepare for the serious end of the forecast and hope for the milder one. That is exactly the posture the Japanese authorities are taking, and it is the right one. There is also the question of what happens beyond Okinawa. As the storm continues toward the waters south of the main Japanese islands, toward Tosa Bay and Shikoku, it is expected to keep weakening, and the threat there is more likely to be heavy rain, rough seas, and gusty winds than a direct strike by a powerful typhoon. But again, the further out you go in a forecast, the more the uncertainty grows, and a storm's exact behaviour several days out, after a complex recurvature, is never something to take for granted. The people of mainland Japan are watching, and the forecasters are refining the track with every new run of the models. There's one more wrinkle in the intensity forecast worth mentioning, because it's a real source of the uncertainty and most people have never heard of it. Powerful mature typhoons sometimes go through something called an eye wall replacement cycle. The compact ring of intense thunderstorms around the eye wall can be surrounded by a second, larger ring that forms further out, and that outer ring can choke off the inner one and gradually take its place. While that's happening, the storm usually weakens temporarily, its winds easing as the inner eye wall collapses, and then it can re-intensify once the new, larger eye wall takes over, often becoming a broader storm in the process. These cycles are common in the stronger storms. They're difficult to predict in advance, and they can cause a powerful typhoon's intensity to swing up and down over a day or two, in ways that complicate the forecast considerably. For a storm like Mekkhala, an eye-wall replacement cycle at the wrong moment could mean it arrives at the islands weaker than its peak, or it could mean the storm grows larger and spreads its strong winds over a wider area even as the peak wind eases. It's one more reason the precise intensity at arrival carries genuine uncertainty, and one more thing the forecasters are watching closely. All of this is why the people whose job it is to forecast these storms speak in ranges and probabilities, rather than single certain numbers, and why the right way to read their guidance is to focus on the range they give rather than fixating on any single headline figure. The storm will do what the warm water, the shear, the outflow, and its own internal structure tell it to do, and several of those variables can't be pinned down precisely days in advance. The honest forecast is a cone of possibility, not a single line, and the wise response is to prepare for the dangerous end of that cone while hoping for the gentle end. That's not forecasters hedging, that's forecasters being truthful about a genuinely uncertain system. So that is where Mekkhala is going. It is curving away from the Philippines, carried north and then northeast by the edge of a subtropical ridge, aimed at the Sakishima Islands and Okinawa, around the 25th and 26th of June, most likely weakening from its peak but carrying real uncertainty about just how much. Millions of well-prepared but justifiably anxious people sit in its potential path, doing what coastal populations have always done when a storm turns toward them, which is to prepare, to watch, and to wait. But there's a question hanging over all of this, the question we keep coming back to, and it's the one I want to tackle next. Because everything I've just described, the strength, the speed, the timing, all of it hinges on that 22-year figure, on the claim that we haven't seen a June typhoon like this in more than 2 decades. So let's actually go back 22 years. Let's look at the last storm that did this, what it was, what it did, and what it might be able to tell us about the one bearing down on Japan right now. Because the last time the Pacific built a June typhoon this strong, the story did not end quietly. Part 5. The last time. This happened. 22 years is a strange unit of time. It's long enough that an entire generation has grown up without seeing the thing in question, long enough that the institutional memory starts to fade, long enough that when it happens again, it catches people off guard. So when forecasters say Mekkhala is the strongest June typhoon in 22 years, they're reaching back to a storm that most people watching this have never heard of, a storm from the year 2004. And to understand what Mekkhala's record really means, we have to go back and meet that storm, because the comparison is both reassuring and unsettling, and you should hold both of those feelings at once. The storm was called Dianmu. In the Philippines, where it passed through the area of responsibility, it carried the local name Helen, just as Mekkhala carries the name Francisco. And in June of 2004, Dianmu did almost exactly what Mekkhala is doing now. It formed in the Western Pacific, and it underwent rapid intensification, climbing in a matter of days from a modest system into a genuine super typhoon. At its peak, Dianmu was a beast. Its maximum sustained winds were estimated as high as 155 to 180 knots, and its central pressure fell to around 915 hectopascals. To put that in perspective, that is meaningfully stronger than the peak that Mekkhala has reached so far, a top-tier super typhoon by any measure, one of the most intense storms of its entire year. And it reached that strength in June, the same out-of-season month that's making Mekkhala such a striking event right now. Dianmu went on to affect southeastern Japan, tracking toward the same general part of the world that Mekkhala is now aiming for. So the parallel is close. An explosively intensifying June super typhoon in the Western Pacific curving toward Japan. The last time that specific combination occurred, it was Dianmu 22 years ago. And the fact that we have to go back that far to find the match is exactly what makes Mekkhala newsworthy. But here's the first thing the comparison should teach you, and it's the reassuring part. June super typhoons, while rare, are not unprecedented. They have happened before. The Western Pacific is capable of producing this kind of storm in this kind of month, and it has done so within living memory. Mekkhala is not a violation of the laws of nature. It is a rare event drawn from a distribution that includes rare events. The ocean did not break. It did something unusual, something it does roughly once in a generation, and 22 years ago it did something even more extreme. So if part of you was wondering whether Mekkhala represents some impossible, off-the-charts anomaly, the honest answer is no. It represents the high end of what the basin can do, and the basin has reached that high end before. Now here's the unsettling part, and it's where the comparison stops being reassuring. The year 2004 was not a quiet year for typhoons. It was, by the measures we use, one of the most intense Western Pacific seasons in the entire modern record. That season produced an extraordinary number of storms, including roughly 6 super typhoons, and it ranks among the most active and most intense seasons ever documented in that basin. Dianmu, the June super typhoon, was not a lonely outlier in an otherwise calm year. It was the early explosive opening act of a season that went on to be a relentless, record-setting parade of powerful storms. Sit with that for a moment, because this is the part that connects back to everything we've been building toward. The last time the Western Pacific produced a June typhoon as strong as Mekkhala, that early super typhoon was the leading edge of one of the most ferocious typhoon seasons on record. The June monster was a preview. It was the basin announcing early that the conditions were primed for an extreme year, and the rest of the year delivered on that announcement. I want to be extremely careful here, because this is the exact point where it would be easy to slide from analysis into prophecy, and I'm not going to do that. One historical parallel is not a forecast. The fact that the last comparable June super typhoon preceded an extreme season does not mean this one will. 2004 and 2026 are different years, with different ocean states, different atmospheric patterns, different everything. You cannot take a single previous case and use it to predict the future. That would be exactly the kind of overreach this channel refuses to do. The sample size is 1. One example proves nothing about what comes next. But, and this is the honest tension I want to leave you holding, the logic underneath the parallel is not nothing. The reason an early super typhoon can be a preview of an active season is not magic, and it's not coincidence. It's the same logic we built in the chapter on ocean heat. An early explosive storm is a sign that the basin is already primed, already loaded with warm water and favourable conditions earlier than usual. And the conditions that allow an early super typhoon to form, the deep ocean heat, the warm sea surface, don't vanish after the storm passes. They persist. The same warm, loaded basin that built the June storm is still sitting there for July, August, September and October, the heart of the season. So while one historical case can't predict the future, the physical reason behind the historical pattern, the persistence of the underlying ocean conditions, is real, and it applies right now. The Pacific that built Mekkhala in June is the Pacific that the rest of the season will be drawing from. That is why forecasters and scientists pay attention to early season extremes. Not because one storm foretells the future, but because an early extreme is a measurement of the basin's state, and the basin state is the thing that loads the dice for every storm that follows. Mekkhala is telling us, the way Dianmu told us 22 years ago, that the Western Pacific is holding a lot of heat and is capable of producing top-tier storms right now. What the rest of this season does with that loaded basin remains to be written, and I'm not going to write it for you in advance. But I would be lying if I told you that an early super typhoon in a warming, primed Pacific was a comforting sign for the months ahead. It is the opposite of comforting. It is a basin showing its strength early. There's one more dimension to the 2004 comparison that's worth drawing out, because it speaks to how our understanding has changed. 22 years ago, our ability to observe these storms in real time, to measure their intensification, to forecast their tracks, was real but more limited than what we have today. We now watch these storms with a density of satellite coverage and a sophistication of modelling that would have been the envy of forecasters in 2004. And yet, even with all those tools, Mekkhala's rapid intensification still partly outran the early forecasts, still surprised the people watching it, still climbed faster than the initial projection suggested. That's a humbling thing to notice. With all our instruments and all our models, an explosively intensifying storm is still capable of moving faster than our predictions, which is a reminder of how much raw power these systems carry and how much respect they demand. The lesson of rapid intensification, the lesson that the gap between forecast and reality is where the danger lives, is a lesson we are still learning, 22 years after Dianmu and right now, today, with Mekkhala. So the 22-year record means two things at once, and you should carry both. It means this kind of storm is rare, a once-in-a-generation event for the month of June, which should reassure you that the world is not ending, and the ocean is behaving within the bounds of what it has always been capable of. And it means this kind of storm, the last time it appeared, was the opening act of one of the most intense seasons on record, which should sober you about what a loaded, warming basin might have in store for the months ahead. Rare, but a marker. Unusual, but a signal. That is what 22 years buys you when you actually look at what was sitting at the other end of it. I want to add a little more texture to just how unusual a June super typhoon actually is, because the 22-year figure can wash over you if you don't slow down and feel it. The Western Pacific produces, in a typical year, dozens of named storms and a good number of typhoons, and a meaningful handful of those reach super typhoon strength. But almost all of that intensity is concentrated in the late season window, the stretch from late summer into autumn, when the ocean has finished charging. The number of storms that reach the very top tier specifically in June, across the decades of the modern record, is small. They are the exceptions, the cases that stand out precisely because they arrived before the basin was supposed to be ready. To find the last one as strong as Mekkhala, you have to go back through more than 2 decades of seasons, through hundreds upon hundreds of storms, before you land on a June match. That's how far down the tail of the distribution this event sits, and the storm at the other end of that 22-year reach, Dianmu, is worth one more look, because the 2004 season it opened is a genuine cautionary tale about what a primed basin can do. That season didn't just produce a lot of storms, it produced an extraordinary run of powerful ones, a relentless procession that battered the Western Pacific from early in the year through the autumn, with a number of super typhoons and a level of accumulated intensity that put it among the most ferocious seasons ever recorded. For the countries of the region, it was a long, exhausting year of storm after storm with little respite between them. The June super typhoon was the overture, and the symphony that followed was brutal. None of that means this season will follow the same script, and I keep saying so because it's true. But it does illustrate, concretely, what it can look like when a basin announces its strength early, and then keeps that strength through the heart of the season. The right way to use a historical analogue, I think, is not as a crystal ball, but as a reference class, a way of understanding what category of event you're looking at. Mekkhala belongs to the category of early season super typhoons in the Western Pacific, a small and rare category, and the members of that category have, at times, been associated with active and dangerous seasons for the physical reasons we've discussed about persistent ocean heat. That doesn't predict this season, it tells you what kind of thing you're watching, and what kind of thing it has sometimes preceded, so you can hold the right level of attention. The reference class doesn't give you the future, it gives you the stakes, and the stakes, when an early super typhoon appears in a warm and loaded basin, are high enough to be worth every bit of attention we can give them. Now, whenever a storm like this commands the world's attention, something else always happens alongside the legitimate science and the genuine concern. A different kind of story starts to spread, a story that says the truth is being hidden, or that the storm itself is not natural, that someone built it or steered it, or is concealing how strong it really is. These claims show up like clockwork every time a major typhoon or hurricane threatens a populated coast, and Mekkhala is no exception. I think it's worth taking those claims seriously enough to actually examine them, not to mock the people who raise them, because the impulse behind them is understandable, but to walk through what the science actually says. So let's do that. Let's talk about the theories swirling around this storm, where they come from, and where the evidence actually leads. Part 6. The stories people tell about storms. Every time a powerful storm turns toward a populated coast, a second storm forms alongside it, and that second storm is made of stories. It spreads online, it moves faster than the typhoon itself, and it tells people that what they're seeing is not what they're being told. Mekkhala has its own version of this, and I want to walk through it honestly because the worst thing I could do is pretend these claims don't exist, and the second worst thing I could do is mock the people who find them compelling. So let's take them seriously, one at a time, and follow the evidence wherever it actually goes. The first claim, the one that surfaces with almost every major storm now, is that the typhoon is not natural, that it was created or steered or intensified deliberately by some program of weather modification, often tied to ideas about ionospheric heating facilities or directed energy or large-scale geoengineering. The specific flavour varies, but the core idea is the same. Someone is doing this on purpose, and the storm's path toward a particular target is evidence of intent. I understand why this idea has pull. When something this enormous and this threatening bears down on you, The notion that it's random, that the universe simply rolled the dice and your coastline came up, can feel more frightening than the idea that someone is behind it. At least a controlled storm implies a controller, an intelligence, maybe even a possibility of negotiation or prevention. Pure indifferent physics offers no such comfort. So the impulse to find an author behind the storm is deeply human, and I'm not going to insult anyone for feeling it. But let's look at what it would actually require, because this is where the idea collapses under its own weight. I told you earlier about the energy these storms release, and I want you to hold on to that number now because it's the whole answer. A mature typhoon releases heat energy at a rate hundreds of times greater than the entire electricity-generating capacity of human civilization. Not once. Continuously, every second, for days on end. There is no facility, no technology, no program on Earth that produces, or could produce, or could even meaningfully nudge, energy on that scale. We cannot build a machine that creates a typhoon for the same reason we cannot build a machine that lights a second sun. The energy budget is not even in the same universe as our capabilities. To create or power one of these storms, you would need to outproduce the entire human race's energy output by a factor of hundreds, and do it over a patch of open ocean, invisibly. It is not a question of secrecy. It is a question of physics, and the physics says no. What about steering it then? Maybe not creating the storm, but nudging its path toward a target. Here the answer is just as clean, and we already covered the mechanism. Mekkhala's track is governed by the subtropical ridge, that vast dome of high pressure I described, and the storm's recurvature toward Japan is the textbook behaviour of a storm riding the western edge of that ridge. It is the single most common track shape in the entire basin. Storms have been recurving toward Japan along exactly this path for as long as we have records, for as long as there have been people watching the sky over those islands, long before anyone had the technology that the steering theories invoke. The path isn't evidence of intent. It's evidence of meteorology working exactly the way it always has. To believe the storm is being steered, you'd have to believe someone is also manufacturing the continent-spanning pressure pattern that does the steering, which brings us right back to the impossible energy budget. The second claim is subtler, and it deserves a more careful answer, because there's a kernel of something real inside it that the conspiracy version distorts. The claim is that the authorities are hiding the storm's true strength, that the official numbers are wrong, that the real intensity is being concealed for some reason. And here's the thing, there is a real fact underneath this claim, and it's a fact I've already told you. The intensity of a storm out in the open ocean genuinely is uncertain. It really is largely estimated from satellite imagery, rather than measured directly, because you can't easily put instruments inside a typhoon in the middle of the Philippine Sea. Different agencies looking at the same storm really do sometimes arrive at somewhat different intensity numbers, so the people who sense that there's some fuzziness in the numbers are not imagining it. The fuzziness is real. But here's where the conspiracy interpretation gets the story exactly backwards. The uncertainty in storm intensity is not hidden. It is openly acknowledged, built into the science, discussed by the forecasters themselves. And far from a single authority concealing the truth, Mekkhala is being tracked simultaneously by multiple independent agencies: the Joint Typhoon Warning Center, the Japan Meteorological Agency, PAGASA in the Philippines, each producing its own estimates, each publicly available, each cross-checking the others. If anyone were trying to hide the real numbers, they would have to coordinate a silence across multiple national agencies that don't answer to the same authorities and that have every professional incentive to get the forecast right, because their credibility and people's lives depend on it. The reality is the opposite of concealment. It's a system of overlapping, transparent, independently produced estimates, openly labelled with their uncertainty. The disagreement between agencies that the conspiracy reads as evidence of a cover-up is actually evidence of an honest scientific process, multiple groups making their best independent estimate of a quantity that is genuinely hard to measure and showing their work. And remember the three names: Mekkhala, Francisco, 07W. To someone primed to see concealment, three names for one storm can look like obfuscation, like the truth being split up and hidden. But it's the opposite. The international name, the Philippine name, and the technical designation exist because multiple agencies in multiple countries are all openly tracking the same storm and naming it according to their own established systems. The multiplicity of names is a fingerprint of transparency, not secrecy. It's what it looks like when several independent bodies are all watching the same thing in the open. So where does that leave us? It leaves us with a storm that is exactly what the science says it is. A natural system, built by warm water and favourable winds, steered by a pressure pattern that has guided storms along this path for all of recorded history, tracked openly by multiple independent agencies whose honest disagreement about the precise wind speed reflects the real and disclosed difficulty of measuring a storm from space. There is no hidden hand. There is no concealed number. There is something arguably more unsettling than either, which is an ocean that is genuinely, measurably warmer and more primed than it used to be, producing a genuinely rare and genuinely dangerous storm entirely on its own, with no author and no off switch. The truth about Mekkhala is not that someone built it. The truth is that nobody had to. I'll say one more thing about this, because it matters for how you carry yourself through a world full of these stories. The reason to reject the conspiracy version is not that it's disrespectful to ask questions. Asking questions is the entire point of science, and skepticism toward authority is healthy and necessary. The reason to reject it is that when you actually do the work, when you actually follow the energy budget and the steering physics and the structure of how these storms are observed, the evidence leads somewhere specific, and it doesn't lead to a secret weather weapon. It leads to the ocean. And the ocean story, the real one, is more important and more actionable than any conspiracy, because the ocean's warmth is something we can actually measure, actually understand, and actually reckon with. The conspiracy is a distraction from the real and more difficult truth sitting in plain sight in the sea surface temperature data. There's a second kind of overclaim I want to address before we move on, because it comes from the opposite direction, and it's just as much a distortion as the conspiracy version, even though it tends to come from people who consider themselves on the side of the science. That's the impulse to seize on a storm like this and declare it definitive proof of climate catastrophe. To say, look, here it is, the smoking gun, the undeniable evidence that the world is ending. And I understand that impulse too, because the underlying concern about a warming ocean is legitimate and grounded in real physics, as we've spent this whole video establishing. But the leap from this storm fits the pattern. To this storm proves the catastrophe is exactly the same logical error the conspiracy theorists make, just pointed in a different direction. It takes a single event and treats it as proof of a sweeping conclusion, and a single event can't do that, no matter which conclusion you want it to support. Here's the symmetry that I find genuinely clarifying. The person who says this storm was manufactured by a secret weather weapon, and the person who says this storm proves we're all doomed, are making the same mistake. Both are taking one dramatic event and loading it with a certainty it cannot carry. Both are skipping the hard, patient work of looking at the full sequence of evidence and jumping straight to the conclusion that confirms what they already believed. The storm becomes a mirror, reflecting back whatever the viewer brought to it. And in both cases, the actual storm, the real physical event with its real and interesting and uncertain story, gets lost behind the certainty people project onto it. The discipline this channel tries to practice, and that I gently encourage you to practice too, is to resist both leaps. To let the storm be what it actually is, no more and no less. And what it actually is a single, well-observed, genuinely rare event that is consistent with a warming ocean pattern that scientists are carefully tracking, that proves nothing on its own, and that earns its place in a sequence we should all keep watching. That framing isn't as satisfying as either the secret weapon story or the end is here story. It doesn't give you a villain or a verdict. It gives you a data point and an open question, which is a harder thing to sit with, because human beings crave resolution, and a data point with an open question offers none. But it's the truth, and the truth is the only thing worth building your understanding on. The conspiracy gives you a false enemy. The apocalypse gives you a false certainty. The honest middle gives you something less comfortable and far more useful, which is an accurate picture of what we know, what we don't, and what we should be watching for. I labour this point because how you hold an event like this matters beyond this single storm. If you train yourself to treat every dramatic weather event as proof of whatever you already believe, you will learn nothing from any of them, because you'll only ever see your own assumptions reflected back. But if you train yourself to ask what a given event actually demonstrates, and to hold the difference between fits the pattern and proves the case, then each storm becomes a genuine piece of information, and the accumulating sequence of them becomes a real education in the state of the planet. That's the habit of mind I'm actually trying to build here, storm after storm. Not a set of conclusions to memorize, but a way of looking that can handle uncertainty without either collapsing into denial or inflating into panic. Mekkhala is a good teacher for that habit precisely because it sits in the honest middle, undeniably remarkable, genuinely consistent with the warming pattern, and yet, on its own, proof of nothing. Learn to hold it that way, and you'll be ready to read the storms that come after it. Now, I've been talking about Mekkhala as if it were alone out there, the single dramatic event in an otherwise empty world. But it isn't alone. At the very same time this storm was exploding in the Philippine Sea, the rest of the planet's oceans were doing things of their own, and the contrast between them is its own remarkable story, one that sharpens everything we've said about how primed the Western Pacific has become. So let's pull back the lens, look at the whole board, and see what the other oceans were doing while Mekkhala was busy becoming the strongest June typhoon in 22 years. Part 7. Two Oceans, Two Different Worlds. If you could float above the planet for a moment and look down at all the world's oceans at once, on this particular day in late June, you would see something that looks almost like a deliberate contrast, as if someone had arranged the two great storm basins of the Northern Hemisphere to make a point. On one side, the Western Pacific is alive, churning, producing not one but two named systems and building a near super typhoon. On the other side, the Atlantic is dead silent, suppressed, holding nothing at all. The difference between them is not random, and once you understand it, it tells you even more about how loaded the Pacific has become. Let's start with the Pacific because Mekkhala isn't the only storm out there. At the same time it was intensifying east of Luzon, a second system was spinning to its east, near the Mariana Islands. That storm carries the designation 08W and the name Higos, and while it's far weaker than Mekkhala, it was strong enough to prompt a tropical storm warning for the western coastal waters of Tinian and Saipan, with tropical storm force winds and hazardous seas. Higos is the smaller sibling here, nowhere near the monster that Mekkhala became, but its presence matters for the bigger picture, because it means the Western Pacific in late June was running two simultaneous named storms. The basin wasn't producing one freak event in an otherwise quiet ocean. It was active, broadly, across a wide stretch of water, which is exactly what you'd expect from a basin that's warm and primed, rather than one that got unlucky in a single spot. This is the part of the Pacific we've talked about before on this channel, the stretch around the Marianas and Guam that sits in one of the most storm-exposed positions on the planet. We've covered earlier this season how this region becomes a target for some of the most violent storms the Pacific produces, and how the communities there, including significant infrastructure, sit directly in the path of the basin's worst. Higos is a gentler visitor than the storms we discussed then, but it's a reminder that this corner of the ocean is rarely quiet for long, and that the Western Pacific storm machine runs broad and runs early when the conditions are right. Now cross the planet to the Atlantic, and you find the opposite of all this energy. On this same day, the National Hurricane Center expected no tropical cyclone formation anywhere in the Atlantic basin over the following 7 days. Nothing. A whole week of forecast and not a single system given meaningful odds of developing. And the Atlantic wasn't just quiet by chance. It was being actively suppressed, held down by a specific and visible force, a vast plume of dry, dusty air streaming westward off the Sahara Desert and pushing across the tropical Atlantic into the Caribbean and toward Florida. This Saharan air is one of the most effective natural storm killers on the planet, and the way it works is worth understanding, because it's the mirror image of everything that built Mekkhala. Tropical cyclones need deep, moist air to feed their thunderstorms, the same moisture and condensation engine we talked about. The air streaming off the Sahara is the opposite of what they need. It's bone dry, and that dryness chokes the developing thunderstorms, starving them of the moisture they need to build. The Saharan air also tends to come with its own embedded winds that add shear, tearing at any system trying to organise, and the dust itself can subtly alter the atmosphere in ways that further discourage storm formation. When a thick Saharan plume is parked over the tropical Atlantic, as it was on this day, it effectively slams the door on storm development across a huge swathe of ocean. The Atlantic wasn't merely failing to produce storms, it was being held down. So here is the contrast in full. Two great ocean basins on the same planet on the same calendar day. One is warm, primed, low on shear, and producing multiple storms including a near super typhoon that exploded overnight. The other is being smothered by dry desert air and forecast to produce nothing at all for a week. And the contrast isn't just a curiosity. It's a vivid, visible illustration of how much the local state of an ocean basin governs what it produces. Storms are not handed out evenly across the world. They form where the conditions allow, and right now, the conditions in the Western Pacific are about as favourable as they get, while the conditions in the Atlantic are about as hostile as they get. The same global atmosphere, two completely different outcomes, decided entirely by the local state of the water and the air above it. And that contrast circles us right back to the thread that runs through this whole story. Mekkhala is what a primed favourable basin produces, and the Western Pacific is that basin right now. The Atlantic shows you the flip side, what happens when the conditions turn hostile, and it makes the Pacific's productivity all the more striking by comparison. When you see one ocean shut down completely while the other manufactures a record June typhoon, you're watching, in real time, just how decisive the state of the ocean is in determining where the planet's most powerful weather gets born. Let me bring this back down to the ground though, because while the global picture is fascinating, Mekkhala is a real storm affecting real places beyond just Okinawa and Japan, and those places deserve a mention. As the storm tracks through the Philippine Sea and begins its recurvature, its influence radiates outward well beyond the centre. For the northern Philippines, even though the storm is forecast to stay offshore and spare Luzon a direct hit, the system's circulation can enhance the seasonal monsoon, drawing in moisture and wringing it out as heavy rain over parts of the north. That brings the threat of flooding and rough seas to coastal and low-lying areas, the kind of indirect hazard that a powerful offshore storm can deliver even without making landfall. The storm doesn't have to come ashore to make the ocean dangerous, and the rain heavy along the coast it passes. For Taiwan, sitting just to the west of the storm's projected path, the main concern is the sea. A powerful typhoon churning through nearby waters generates enormous swells and hazardous marine conditions, and depending on exactly how the track evolves, sea warnings for the waters around Taiwan are a real possibility. The island itself may be spared the storm's core, but the ocean around it feels a storm like this from a long way off. And as for Vietnam, further to the west, the current forecast carries no immediate threat. Mekkhala's recurvature takes it away from the South China Sea and toward Japan, which means the mainland coast of Southeast Asia is, for this storm, out of the firing line. That's worth stating plainly, because in a region that knows the devastation typhoons can bring, knowing which storms are coming for you and which ones are turning away is the difference that lets people breathe. So the storm's reach is wide. Heavy rain and rough seas brushing the northern Philippines, hazardous waters threatening the seas around Taiwan, the main blow aimed at Okinawa and the Ryukyus, and a weakening tail trailing toward mainland Japan, all while a second system stirs near the Marianas and the Atlantic lies dead beneath a blanket of desert dust. That's the full board. That's everything the oceans were doing while Mekkhala became the strongest June typhoon in more than 2 decades. But we still haven't answered the biggest question, the one that's been sitting underneath every chapter of this story. We know what Mekkhala is. We know how it formed, where it's going, what came before it, and what's happening around it. The question we haven't fully faced is what it means. What does it mean that the Pacific built this storm in June? What is an early super typhoon actually telling us about the season ahead and the years ahead? That's the question I want to end on, because it's the one that matters long after this particular storm has spun itself out over the cool waters north of Japan. So let's face it directly. Part 8. What an early monster means. There's a temptation, when a single dramatic storm grabs the world's attention, to treat it as a self-contained event. The storm forms, the storm threatens, the storm passes, and we move on, filing it away as one more weather story among thousands. But some storms are more than events. Some storms are measurements, and Mekkhala is one of them. To understand what it's measuring, you have to stop thinking of it as a thing that happened, and start thinking of it as a reading on an instrument, the instrument being the entire Western Pacific. Here is the core of it, the idea I've been building toward through this whole video. The strength a storm can reach is limited by the conditions around it. Warm water, low shear, good outflow, those set a ceiling on how intense any storm in that environment can become. When a storm reaches an extreme intensity, it is by definition telling you that the ceiling in that place was extremely high. And when a storm reaches an extreme intensity early, In a month like June, when the ceiling is normally still rising toward its late summer peak, it's telling you that the ceiling got high ahead of schedule. The basin became capable of producing a monster before it was supposed to. That's what an early super typhoon measures. Not just that a storm happened, but that the conditions for a monster were already in place, weeks or months ahead of the calendar. And the conditions that set that ceiling, the warm, deep ocean heat especially, don't evaporate when the storm moves on. The atmosphere changes from week to week, the shear comes and goes, but the ocean's heat is the slow, persistent foundation underneath all of it. The warm water that gave Mekkhala its high ceiling in June is going to be sitting in that basin, and warming further as the season moves into its traditional peak. So the early super typhoon isn't just a measurement of June, it's a measurement of a foundation that will still be there in July, in August, in September, when the atmospheric conditions are even more likely to align and let storms reach the ceiling that the ocean allows. That's the real reason an early extreme matters. It's not a prophecy, it's a foundation reading, and the foundation persists. This is exactly the logic that made the 2004 parallel so resonant. The last June super typhoon was the leading edge of an extreme season, not because the June storm magically caused the rest of the year, but because the June storm revealed a basin that was already primed, and a primed basin tends to stay primed through the months that follow. The same logic applies now. I can't tell you what the rest of this season holds, and I won't pretend to, but I can tell you what Mekkhala has revealed about the state of the foundation, and the foundation is warm, deep, and loaded earlier than usual. Now let me widen the lens one more turn to the longest timescale, because there's a question underneath all of this that I'd be dodging if I didn't name it. Is this kind of early explosive storm becoming more common? Is the calendar window for monsters widening? Is rapid intensification, that most dangerous of storm behaviours, happening more often than it used to? These are among the most actively researched questions in all of climate and atmospheric science right now, and I want to give you the honest state of that research, neither overselling it nor waving it away. The honest state is this. There is substantial scientific work examining whether warming ocean surfaces and rising ocean heat content are increasing the frequency of rapid intensification events and expanding the range of the calendar in which the strongest storms can form. The physical reasoning behind the concern is straightforward and hard to argue with at the level of basic physics. Warmer water means more available fuel. More available fuel means a higher ceiling on storm intensity, and a higher ceiling reached earlier in the year. More fuel also supports the explosive feedback loop of rapid intensification by removing the cool water break that would otherwise slow a storm down. So at the level of mechanism, the idea that a warming ocean would produce more rapid intensification and more out-of-season extremes is not a fringe claim. It's a direct consequence of the physics we've spent this whole video building. What's harder, and where the honest scientist becomes appropriately cautious, is connecting that mechanism to any single storm, or even to short-term trends, because storms are noisy, the record is complicated, and natural variability is large. This is why you'll never hear a careful scientist say a warming ocean caused Mekkhala. They'll say, correctly, that you can't attribute a single storm that way, but you will hear them say that a warming ocean raises the odds of exactly this kind of event, that it loads the dice toward higher intensities and earlier extremes, and that storms like Mekkhala are consistent with what the warming ocean framework predicts we should see more of. That's the careful, honest framing, and it's the one I want to leave you with. Not this storm proves it, but this storm fits. And here's the thing about a single data point fitting a predicted pattern. On its own, it proves nothing, and I've said that several times because it's true and it's important. But data points don't arrive on their own. They arrive in sequences, over years, and the question that matters is not what any single point means, but what the accumulating sequence shows. Mekkhala is one point, the strongest June typhoon in 22 years, forming over water 3 to 4 degrees above the threshold, in a basin that swung warm over the preceding 6 months, undergoing explosive intensification that outran the early forecasts. You file that point away, and you watch for the next one, and the one after that, and over time the sequence either holds to the historical pattern or it drifts towards something new. The reason events like this one are worth stopping for, worth making an entire video about, is not that one storm settles the question. It's that one storm is a chance to see clearly where a single point landed, so that when you look back across the sequence years from now, you'll have actually been paying attention. So what does an early monster mean? It means the Western Pacific reached the capacity for a top-tier storm ahead of schedule. It means the foundation, the ocean heat, is warm and deep and loaded going into the heart of the season. It means we have one more data point, landing right where the warming ocean framework predicts, in a sequence we should all be watching. And it means, for the more immediate and human concern, that a powerful storm is bearing down on a chain of inhabited islands right now, and the people there have to deal not with the long-term pattern, but with the very real storm in front of them. The big picture meaning and the on-the-ground reality coexist. The pattern matters for understanding the years ahead. The storm matters for the people in its path this week. Both are true, and a complete picture holds both at once. I want to spend the last part of this on those people, and on you, because for all the talk of basins and ceilings and data points, this ultimately comes down to human beings looking at a darkening sky and deciding what to do. So let's close by talking about what this storm means for the people who have to live through it, what they should be watching for, and what all of us should take away when the wind finally dies down and Mekkhala becomes another name in the record books. Because how we respond to a storm like this, what we learn from it, is the part of the story we actually get to write ourselves. Part 9. The People in the Path. Strip away the science for a moment, the indices and the ceilings and the data points, and what you're left with is the oldest situation in human history. A community looks out at the horizon, sees a storm coming, and has to decide what to do. Every coastal culture on Earth has lived this moment over and over for as long as people have lived by the sea. And right now, across the southern islands of Japan, that ancient moment is playing out again, with modern tools but the same fundamental stakes. The good news, and I want to lead with it because it's real and it matters, is that few places on the planet are better prepared for a typhoon than Okinawa and the Ryukyu Islands. This is one of the most typhoon-exposed inhabited regions on Earth, and the people there have built their entire civilization around that fact. The buildings are constructed to standards that assume powerful storms will come. Many homes and structures are made of reinforced concrete specifically because it stands up to wind that would tear apart lighter construction. The emergency systems are practiced and refined. The cultural memory of typhoons runs deep, passed down through generations who have all weathered storms like this. When a typhoon approaches Okinawa, it approaches a population that knows exactly what to do, that has done it many times before, and that has infrastructure built for precisely this threat. The preparedness saves lives, and it's the single biggest reason a storm that would be catastrophic on an unprepared coast can strike the Ryukyus and be endured. But preparedness is not the same as safety, and I never want to let reassurance tip over into complacency. A powerful typhoon is dangerous even to the best prepared population on Earth, and the hazards Mekkhala could bring are serious regardless of how ready Okinawa is. The wind can still bring down power lines and leave people in the dark and the heat for days. The storm surge can still flood coastal areas and threaten anyone who hasn't moved to safety. The rainfall, which a storm this size can deliver in enormous quantities, can still trigger flash floods and landslides in the steep island terrain. The seas can still claim anyone who underestimates them, and every year, tragically, storms like this take people who went to look at the waves, or tried to secure a boat, or simply didn't take the warnings seriously enough. Preparedness reduces the toll, it doesn't erase the danger. So what should the people in the path actually be watching over the next few days? The single most important variable is the one we talked about in the chapter on the track, the timing and sharpness of the recurvature. That turn determines exactly how close the storm's core comes to each island, and small shifts in it make large differences on the ground. The forecasters will be refining the track with every new run of their models, and the right move for anyone in the region is to stay locked onto the official guidance from the Japan Meteorological Agency and local authorities, who will be issuing the warnings and advisories calibrated to exactly how the track evolves. The forecast you saw yesterday is not the forecast today, and the forecast today is not the one you'll have tomorrow. These things update, and in a recurving storm the updates matter enormously. The second variable to watch is the intensity at arrival, the question of how much the storm weakens before it reaches the islands. I told you the most likely scenario is meaningful weakening as Mekkhala moves over cooler water and into stronger shear, and that's genuinely the expected outcome. But I also told you that the degree of weakening carries real uncertainty, and that storms have a long history of arriving stronger than the optimistic forecasts hoped. So the wise posture, the one the authorities are taking, is to prepare for the serious end of the range and be grateful if the milder end is what shows up. You prepare for the strong storm and you hope for the weak one. You do not prepare for the weak one and hope the strong one stays away. That asymmetry, prepare for the worst plausible case, is the entire logic of storm preparedness, and it exists precisely because of stories like the rapid intensification we watched at the start of this one. Stories where the gap between what people expected and what arrived is where the tragedy lived. And that brings me to the deepest lesson of this whole event, the one that applies far beyond Okinawa, far beyond this single storm. Mekkhala's defining feature was the speed of its intensification, the way it outran the early forecasts and surprised even the professionals watching it. That speed is the thing to internalize, because it's becoming a defining feature of the storm threat in general. The old mental model, where a storm gives you days of clear warning at a steady, predictable strength, is increasingly unreliable. The new reality includes storms that can blow up in the final hours, that can be one thing when you go to bed and a far more dangerous thing when you wake up. And the only defense against a storm that can intensify faster than the forecast is to take the threat seriously early, before the explosion, when there's still time to act. By the time a rapidly intensifying storm reveals its full strength, the window to prepare may already be closing. The lesson of rapid intensification is to respect the early warning, even when the storm in front of you still looks manageable, because the storm in front of you is not necessarily the storm that will arrive. I want to say something to the wider audience now, the people watching this who are nowhere near Japan, who will never feel a single gust of Mekkhala's wind. You might wonder why a storm on the other side of the world should matter to you, and it's a fair question. Here's my answer. Mekkhala matters to you because it's a clear, legible signal of the state of the planet's oceans, and the state of the planet's oceans matters to everyone, everywhere, eventually. The same warming that primed the Western Pacific to build a June super typhoon is a global phenomenon, and the basins near you, wherever you are subject to the same fundamental physics. The Atlantic that lies dead under Saharan dust today will not stay quiet all season, and when it wakes, it will be drawing on its own reservoir of ocean heat. The lessons Mekkhala teaches about how fast storms can intensify, about how early the season can load, about how the ocean's warmth sets the ceiling, are lessons that apply to every storm-prone coast on Earth, including, quite possibly, yours. A storm in the Philippine Sea is a window into a process that's unfolding planet-wide. And there's something else, something simpler and more human. Paying attention to a storm like this, even from far away, is a way of staying connected to the actual physical state of the world we all share. It's easy to live entirely inside the human-built world of screens and schedules, and forget that underneath all of it, the ocean is warming, the atmosphere is shifting, and the planet is doing things on a scale that dwarfs anything we've built. A storm like Mekkhala is a reminder of that larger reality, the one that was here before us and will be here after us, the one we are nudging in ways we're still struggling to fully understand. To watch it carefully, to try to understand it honestly, is to take that larger reality seriously, and I think taking it seriously is one of the most important things any of us can do right now. Let me get specific for a moment about the layered nature of an island typhoon's hazards, because for a chain like the Rukius, the danger doesn't come from one direction. It comes from several at once, and understanding the layers helps you understand why the warnings cover so much. The first layer is the wind, the most obvious threat, capable of stripping roofs, downing trees and power lines and turning anything loose into a projectile moving at deadly speed. The second layer is the storm surge, the dome of seawater the storm's winds pile up and shove onto the coast, which historically has been the single deadliest element of tropical cyclones worldwide, because water is heavy and relentless and floods the low ground where people live. The third layer is the rain, which a storm this size can deliver in quantities measured in feet, overwhelming drainage and triggering flash floods on the flats and landslides on the slopes. And the fourth layer, especially for islands, is the sea state itself, the enormous waves that radiate outward from a powerful storm and make the coast and the water lethal even at a distance from the centre. For an island, those layers compound in a particular way, because there is no inland refuge that is truly far from the sea. On a large continental landmass, you can move people well away from the coast and escape the surge and the waves entirely. On an island, everywhere is, in some sense, the coast. The steep terrain that makes the Ryukyus beautiful also makes them prone to landslides when the rain comes hard, and the surrounding water that defines island life also surrounds island life with the storm's marine hazards. This is why island populations in typhoon country develop such deep cultures of preparedness, and why the warnings issued for a storm like this are so comprehensive, covering wind and water and rain and sea all at once. The hazard isn't a single thing to brace against. It's a stack of things arriving together. There's also a human, psychological dimension to storm preparedness that's worth naming, because it's where a lot of the real danger actually lives. People are remarkably good at talking themselves out of taking a threat seriously, especially a threat they've survived before. The very experience that makes a population resilient. Having weathered many storms can also breed a dangerous complacency, a sense that this one will be like the others, that the warnings are overblown, that staying put will be fine because it was fine last time. Forecasters and emergency managers fight this constantly, and it's one of the reasons rapid intensification is so deadly, because it can turn the storm that's just like the others into a storm that very much isn't, faster than complacent expectations can update. The discipline of taking each storm seriously on its own terms, of respecting the forecast even when the storm in front of you looks familiar, is harder than it sounds, and it's exactly the discipline a rapidly intensifying storm punishes the absence of. So to the people in the path, watch the official forecasts, respect the warnings, prepare for the serious end of the range, and stay safe through the next few days. And to everyone else, watch this storm as what it is, not just a distant disaster but a signal, a reading on the state of an ocean that belongs to all of us. Because when the wind finally dies, and Mekkhala fades into the record as the strongest June typhoon in 22 years, the question it raised won't fade with it. That question will still be sitting there, in the warm water of the Western Pacific, waiting for the next storm to ask it again. And what that question is, and why it should change how you see every storm that comes after this one, is where I want to end. Part 10. The hardest forecast in science. There's a quiet irony sitting at the centre of this entire story, and I've hinted at it a few times, but now I want to put it right out in the open. We live in an age of astonishing observational power. We have satellites watching every patch of ocean. We have computer models running on machines of staggering capability. We have a scientific understanding of these storms that would have seemed like magic to forecasters a century ago. And yet, with all of that, Mekkhala still surprised us. It still intensified faster than the early forecast called for. The single most dangerous thing a storm can do, rapid intensification, remains one of the hardest things in all of science to predict, and understanding why is its own kind of window into how these storms work and how much respect they deserve. Let me explain the nature of the problem because it's genuinely fascinating. Forecasting where a storm will go, the track, has gotten dramatically better over the decades. Track forecasts today are remarkably accurate, often nailing a storm's path days in advance because the track is governed by the large-scale steering flow, those big, relatively predictable features like the subtropical ridge we discussed. Big features are easier to model. But forecasting how strong a storm will get, the intensity, has lagged far behind, and the reason is that intensity is governed by processes happening on much smaller scales, inside the storm's core, in the eye wall, in the precise interaction between the storm and the patch of ocean directly beneath it. Those small-scale internal processes are devilishly hard to observe in detail and even harder to model. The result is that we can often tell you with confidence where a storm is going while struggling to tell you how strong it will be when it gets there. We've largely solved the where. The how strong remains stubbornly open. And rapid intensification is the very worst case of this problem, the place where our predictive ability is weakest exactly when the stakes are highest. The conditions that allow rapid intensification, the warm water, the low shear, the good outflow, we can identify those. We can say a storm is in an environment favourable for rapid intensification, but whether a given storm actually undergoes it, and exactly when, and exactly how fast and how far, depends on those small-scale internal details that we can't fully see or simulate. So forecasters are often in the position of saying rapid intensification is possible, even likely, while being unable to pin down the specifics that would let people prepare for an exact outcome. They can see the loaded gun. They can't always tell you precisely when it will fire or how big the blast will be. Mekkhala is a textbook case. The conditions were clearly favourable, and the forecasters flagged the potential, but the actual intensification, when it came, was explosive enough to partly outrun the early projections, with the storm climbing faster than the initial numbers suggested it would. That's not a failure of the forecasters. They did their job, they flagged the risk, they updated as fast as the data allowed. It's a reflection of how genuinely hard this problem is, how much these storms can still do, that our best science struggles to predict in advance. And it's humbling, because it tells you that even now, even with everything we've built, the ocean and the atmosphere can still produce something faster and stronger than our models expected. The storm is still, in some real sense, ahead of us. This is why the science of rapid intensification is one of the most urgent frontiers in all of atmospheric research. Closing the gap between forecast and reality, even by a few hours, even by a few notches of intensity, would save lives directly, because every hour of accurate warning is an hour that coastal populations can use to prepare and evacuate. Researchers are attacking the problem from every angle, with better satellite instruments that can peer into storm cores, with aircraft that fly directly into storms to measure them where it counts, with new generations of models that try to capture the small-scale physics, with the growing toolkit of pattern recognition applied to the enormous archives of past storms. Progress is being made. But Mekkhala is a reminder of how much frontier is still out there, how much these storms can still do that we can't yet foresee. And here's where this connects back to the warming ocean, because the two problems intersect in a way that should concentrate the mind. If a warming ocean is indeed making rapid intensification more common, as the physics suggests, and the research is investigating, then the storm behaviour that is hardest for us to predict is potentially the behaviour that's becoming more frequent. We would be facing more of exactly the thing we're worst at forecasting. That's a sobering combination, the most dangerous and least predictable storm behaviour potentially increasing in a warming world, and it raises the stakes on the forecasting research enormously. The better we get at predicting rapid intensification, the better we can protect people from a threat that may be growing. The science isn't just academic, it's a race, and the stakes are measured in lives. There's a deeper point hiding in all of this, about the relationship between human knowledge and the natural world, and I think it's worth drawing out because it's easy to come away from a story about satellites and models, thinking we've basically got the planet figured out. We don't. Mekkhala is proof that we don't. For all our instruments, a patch of warm ocean and a favourable sky can still assemble, in a matter of hours, a storm more powerful than anything we build, and less predictable than we'd like to admit. There's a humility in that which I think is genuinely healthy. We are not the masters of this system. We are observers of it. Increasingly skilled observers, but observers nonetheless, watching forces far larger than ourselves and trying imperfectly to understand them well enough to stay out of their way. A storm like Mekkhala puts us back in our proper place, reminds us that the planet is not a machine we operate but a vast dynamic system we inhabit, one that can still surprise the best minds and the best instruments we've got. And maybe that's the right frame for everything we've talked about. The warming ocean, the early super typhoon, the loaded basin, the forecasting frontier, all of it comes back to the same fundamental relationship between a species that has gained enormous power to observe and even to influence the planet, and a planet that remains, in its raw physical force, utterly beyond our control. We can measure the ocean's warming, we can to some degree even drive it through what we put into the atmosphere, but we cannot tell a typhoon where to go or how strong to get or when to fire. We can only watch and prepare and try to understand. Mekkhala sits right at that intersection of human knowledge and natural power, a storm we can see in extraordinary detail and still cannot fully predict, born from an ocean we are warming but cannot command. That intersection, between what we can see and what we can control, between the patterns we can measure and the storms we still can't fully foresee, is where I want to bring this whole story to rest. Because Mekkhala, in the end, is not just a typhoon. It's a question the ocean is asking us, and the question is bigger than any single storm. So let me, finally, try to put that question into words and leave you with the thing I think this storm is really about. Part 11. The Question in the Warm Water. We haven't seen a typhoon this strong in 22 years. Hold that sentence in your mind one more time, because everything we've covered lives inside it. 22 years. More than 2 decades since the Western Pacific built a June storm to match this one. And the second half of that sentence is the part that should stay with you longest. The part that makes this more than a record and turns it into a warning. it's still growing. As I bring this to a close, the storm out there over the Philippine Sea has not finished. It is still feeding on the warm water, still tightening, still climbing toward whatever ceiling the ocean has set for it. The record is already broken, and the storm that broke it isn't done. Let me draw together the thread that's run through every part of this, because it deserves to be stated plainly at the end. This was never just a story about a strong storm hitting Japan, though that storm is real, and the people in its path are facing something serious over the next few days. This was a story about what that storm reveals. Mekkhala is a reading on the state of the Western Pacific, and the reading is high. It tells us the basin is holding more heat, deeper heat, earlier heat than the calendar says it should. It tells us the conditions for a monster were already assembled in June, weeks ahead of the season's traditional peak. And it tells us that the same warm foundation that built this storm is going to be sitting in that ocean, warming further through all the months still to come. The storm is the symptom. The warm, loaded, primed ocean is the condition. And the condition does not pass when the storm does. I've been careful all the way through not to overclaim, and I'm going to hold that line right to the end because the honesty is the whole point. One storm does not prove a trend. Mekkhala does not by itself demonstrate that the world's typhoon seasons are shifting earlier or growing more violent. The last June super typhoon was 22 years ago, which means storms like this are rare, drawn from the high tale of what the ocean has always been capable of, and a single rare event is not a pattern. If you came here looking for me to tell you this one storm proves the future, I won't, because it doesn't, and anyone who tells you otherwise is selling certainty they don't have. But I'll tell you what this storm does do, because it's real, and it's enough. Mekkhala is a data point that lands exactly where the warming ocean framework predicts data points should increasingly land. An early season storm, over water 3 to 4 degrees above the threshold, in a basin that swung warm over 6 months, undergoing rapid intensification that outran the forecasts, reaching a strength the historical record reserves for the heart of the season. Every feature of it fits the pattern that scientists have been describing and watching for. One point on a graph proves nothing. But when a point lands precisely on the line that was drawn years in advance, you take notice, and you watch for the next one. That's not alarmism. That's just paying attention. And paying attention is the entire reason this channel exists. So here is the question I think Mekkhala is really asking, the one sitting in the warm water of the Western Pacific, the one that will outlast this particular storm. Is this a rare alignment, a once-in-a-generation roll of the dice that happened to come up high, the way it did 22 years ago, before things returned to normal? Or is it the early, legible edge of something shifting, the first clearly visible sign that the dice themselves are being reweighted, that the season of monsters is starting earlier and reaching higher than it used to? The honest answer, the only honest answer, is that we cannot yet know from a single storm. The answer is written in the sequence, not the point, and the sequence takes years to read. But the question is real, and it's the right question, and the fact that we have to ask it at all, the fact that a June typhoon can now make us seriously wonder, is itself a kind of answer. Think about what it means that we even have to ask. 22 years ago, a June super typhoon was a remarkable isolated event, and when the season that followed turned out to be extreme, it was understood as the natural variability of a powerful ocean doing what it sometimes does. Today, the same kind of storm arrives into a different context. It arrives into an ocean we know is warming, into a Pacific we've measured swinging warm over just 6 months, into a scientific conversation actively investigating whether the monsters are coming earlier and hitting harder. The storm may be the same kind of storm, but the world it arrives into has changed, and so has the meaning we're forced to give it. That shift in what an early monster means, in the questions we're compelled to ask when we see one, might be the most important change of all. For the people in Okinawa and the Ryukyus, none of this abstraction matters much over the next few days. What matters to them is the wind and the water and the warnings, the concrete business of getting through a powerful storm, and they will do what they've always done, which is prepare, endure and rebuild with a skill and a resilience that the rest of us should learn from. I hope, genuinely, that the forecast weakening holds, that Mekkhala comes down from its peak before it reaches them, that the most likely scenario is the one that plays out, and the islands are spared the worst. We'll be watching to find out, and the answer will come within days. But for the rest of us, Watching from a distance, the storm leaves something behind that won't resolve in days. It leaves the question. And it leaves a way of seeing. Because once you understand that a storm is a reading on the state of an ocean, you can't unsee it. Every storm that comes after this one, you'll find yourself asking the same thing. Not just how strong is it, or where is it going, but what is it telling me about the water it came from? What is the ocean state that it could build this? That question, applied storm after storm, year after year, is how you actually watch a changing planet. Not through any single dramatic event, but through the accumulating pattern that each event reveals a piece of. Mekkhala revealed its piece, the strongest June typhoon in 22 years, still growing as it turns toward Japan, born from an ocean warmer and more loaded than it has any business being this early in the year. The calendar said June, the ocean said otherwise, and the gap between what the calendar expected and what the ocean delivered is, in the end, the whole story, because that gap is where the warning lives. An ocean that produces monsters ahead of schedule is an ocean that has changed the schedule. Whether it has changed it once, by chance, or for good, by something larger, is the question we now get to spend the coming months and years answering, one storm at a time. Mekkhala is the first clear chapter of that answer for this season. It will not be the last. The water is warm, the basin is loaded, and the season has only just begun. Keep your eyes on the Western Pacific. The ocean is talking, and after 22 years, it just said something worth listening to.